Hello and welcome back. We're going to now discuss different type of prediction errors that a machine learning model can make. Let's say we've got a machine learning model that generates predictions for someone whether they are positive for a certain condition, let's say cancer or coronavirus or whatever condition. It's up to you to imagine that, right? So we've got, let's say, a particular person who's got an underlying condition. So I'm going to say whether they're going to be they're positive for that condition. That means they have that condition in. So they are. This is the true label of that, whether a particular person has that condition. And then this is going to be the test output. So this is going to be your prediction output. And this is going to be, so I'm going to call this the prediction, right? So this is going to be the prediction. If a particular person has a condition, and the test says that they have the condition, then we are going to call this true positive. So this is not an error. So not error because the prediction is correct, right? They actually have the condition and the test or your classifier also says that they have that particular condition. Similarly, if they are negative for that condition and your classifier says that, or your test says that they are also negative for that condition, then we are going to say that this is a true negative and similarly, this is not an error, right? The next thing is what happens if they have the condition but your test says or your classifier says that they don't have that condition. So this is going to be a false negative. And this is an error, right? Because the prediction output does not match the true condition, right? And similarly, if you have got a person who doesn't have the condition, but your test says that they do have the condition, so we are going to say this is a false positive, which is another type of error. Some people find these false positive and false negative a bit confusing, and to fix that, I have this sort of, I would say, interesting example that would help you remember what a false positive and a false negative mean. So, if a medical doctor or test says to someone who is male that they're pregnant, then as far as biology is concerned, they're probably this is going to be a false positive, right? It's also called a type 1 error. So false positives are the same as type 1 errors. And if let's say a medical doctor or a test says to a pregnant lady that they're not pregnant, then that is a false negative, right? And this is also called a type 2 error. If you ever find yourself confused, always remember this. So I've seen that students this helps students remember what a false positive and a false negative is. So please go ahead and try to remember that. But the main goal is that we have here is we've got a test, and that test can be a real test in the laboratory, or it can be a test. It can be a machine learning model that generates a particular output or a particular prediction, a binary label of whether a certain person has a certain condition or not, or whether uh, an object has a certain class label or not. Let's say if you got an apple as input to a classifier and out comes the prediction that it's an apple, then we say that this is a correct prediction. But if the input is an apple and the output comes as an orange, then that's an incorrect prediction. Now, depending upon what we assign to the positive class and what we assign to the negative class, the definition of positive or false positives and false negatives can change. But once we have fixed that, once we have assigned, let's say that we are going to call apples as the positive class and oranges as the negative class, then it's really easy to go ahead and uh, assign these definitions of false positives and false negatives. Typically, uh, positive. So if someone is positive for a condition, what that means they have that condition. So in medical informatics, for example, if someone tests positive for a cancer, let's say if you design a machine learning model that analyzes the histopathology image of a person, and we say that they're positive for cancer, then they have, our test is saying that they have the cancer, right? Now, whether they actually have cancer or not, that can be verified through other diagnostic tools. For example, it can be analyzed using biopsy or doctor looking at that biopsy, and then they're going to assign the true label or the ground truth, as it is called, for that particular case. And that is going to help us define whether that prediction generated by the machine learning model is correct or not. But for our purposes at this time, all we need to remember is what is a true positive, true negative, false positive, and false negative. Some people abbreviate it as true positive. This is going to be true negative. This is going to be false positive, FP, and this is going to be false negative. And sometimes we are going to use these abbreviations to indicate how many examples in a given test set are actually true positives, true negatives, false positives, and false negatives. Let's say if you got n examples in your test set in total, and you say that, let's say, n is equal to whatever number, and out of those, this many are predicted correctly. So this is the number of positive examples that are predicted correctly. Then you define that as true positive number, and then you've got these true negatives, which are negative examples that are predicted correctly as negative. So that can be defined as true negative. So that number is called the number of true negative examples. Similarly, you can assign numbers to false positives and false negatives. So I hope this is clear. And on the basis of these, we can now go ahead and define different types of performance metrics, such as accuracy, which is a very simple metric, and you've already calculated that as part of your lab exercises. So accuracy is simply defined as the percentage of correct predictions. Let's say you got a classifier. So you've got a classifier that takes in a particular example and generates its binary label, right? So in goes the example. So we call it X, and out comes the prediction label Y. So I'm going to call this YP, just to discriminate it from Y true, which is the example, which is a true label for a given example, right? So if the classifier is trained, is if it's a binary classifier, that is, it can discriminate between two different classes, then positive and negative, uh, we can have all these true positives, we can have true negatives, we can have false positive and false negative for a given validation or test data set. So we've trained the classifier and then we are testing it on a data set that it has not seen before. And we calculate how many true positives it generates, how many true negatives it generates, how many false positives, and how many false negatives. And on the basis of that, we can define accuracy simply as the percentage of correct predictions, which are true positives and true negatives, divided by the total number of predictions, which is simply the addition of true positive plus true negative plus false positive plus false negative. So this is a total number of, sometimes we abbreviate a total number of examples as n, and out of these, how many predictions are correct, we can express that as a percentage, and that is what we call as accuracy. So let's say if a classifier guesses correctly, if it's given 100 examples during testing, and for 70 of those it correctly predicts their class, then we say that the accuracy of that particular classifier is 70%. Really easy, right? Now that is the easy part. What we are interested in is understanding what are the underlying assumptions that this simple metric is. While when we use this simple metric, what are the assumptions that we are making? So here is a list of assumptions that we are making when we use accuracy. And if these assumptions don't hold, we shouldn't be ideally using accuracy. And this is going to be a recurring theme for different types of metrics in performance assessment of machine learning models. So we are going to talk about a metric, we are going to identify its assumptions, and then for a given problem, the real thing is we're going to see whether those assumptions hold or not. So if the data set is balanced, that means if in the validation data set, the number of positive examples is roughly equal to the number of negative examples, right? So let's say if you've got 100 examples in total, and let's say you've got 50 positive examples and you've got 50 negative examples, then we say that data set is perfectly balanced. And if it is so, then you can go ahead and use accuracy, right? Now, it's important to understand why you can't use accuracy if this is not the case. And this is something I want you to think about. And you may want to pause the video at this point to think about it and come up with your own answer. Okay? And the in general, what we when we're using accuracy, we are making an assumption that misclassification of any class is equally bad. So a positive example being misclassified as a negative example. So if the true label is positive, but the prediction is negative, so this is going to be a false negative, right? And then you've got a negative labeled example, which is being predicted as positive, so that is a false positive. So these two, so this type 1 error, as it is called, right, and this type 2 error, as it is called, both of them have the same impact. And if for a given classification problem or a diagnostic problem, for example, if that is the case, then you can go ahead and use uh, accuracy as a metric. Let me give you an example. So let's say if you classify apples and oranges, or if your classifier classifies apples versus oranges, it takes an example and predicts for that example whether that object is an apple or an orange, and it classifies an apple and as an orange or an orange as an apple. Probably it's not going to make a huge impact, right? So there, since the impact of both of these type 1 and type 2 errors is not large, and it's exactly the same. It doesn't really matter if we flip the labels, right? So there you can go ahead and use accuracy if the data set is also balanced, right? But in other cases, for example, if you're solving a diagnostic problem, and in which case, let's say if a person has a condition, but the classifier misses that, that is, the classifier classifies that person with the positive condition uh, by saying that it does not, or by predicting that they do not have that condition, that can have some serious ramifications, right? So if the underlying condition is, let's say, cold, and let's say a silly classifier misclassifies a person who has a cold as someone who does not have the cold, probably it's not going to be the end of the world for that person, right? But in another problem, let's say if you want, we don't want the classifier, we don't want the classifier to miss if someone has the coronavirus or not, right? Because then that person can go ahead and infect everyone else, right? So we don't want those errors. On the other hand, if by taking the flip of side of that, if a person does not have the condition, but the classifier predicts that they do, then that is a false positive. And let's say based on that classifier's output, we give them a certain treatment. And if that treatment does not have enough, is not costly, or it doesn't affect their health, probably that misclassification is not going to have that much of an impact, right? But in certain cases it might. So this second assumption, when you're using accuracy as a metric, it's always important to understand whether type 1 and what is the impact of type 1 and type 2 errors. So think about it before you start using accuracy. If the impact of the two is going to be similar, then you can go ahead and use accuracy. But I again welcome you to think of where does this assumption come from within this equation. Okay? Probably got to do something with how a true positive and true negative get equal weights in this calculation, in this accuracy calculation, right? But I want you to be to identify that the source of this assumption within this calculation. So that I leave to you. So something for you to ponder on. Then there is this third assumption that I've put over here, that the threshold used for classification is optimal. What threshold and what does that even mean? So we've talked about support vector machines, and we've talked about perceptron, which are linear classifiers, right? And what they do is they don't produce, they can produce a prediction label whether something is above the line or whether something is below the line, right? So if something is above the line, then we say that that is the positive class, and if something is below the line, then we say that it is predicted as negative, right? But in essence, what they do, these classifiers, what they do is, and most of the other classifiers in machine learning, what they do is they take in an example and then they generate a real valued score, as it is called, for that example. And if that score is positive, greater than zero, then we say that that classifier has generated a positive prediction. And if that score from, let's say, in case of a linear classifier, this score W transpose X plus B If that is negative, then we say that that classifier has generated a negative prediction, right? So there, in this simple example, zero is the value that is acting as a threshold. Everything above zero gets classified as positive, and everything below zero gets classified as negative. But we can change this threshold from zero to whatever value we want, right? We can increase the thresholds to say everything above zero point 0.5 is going to be classified as positive, whereas everything below zero point 0.5 is going to be classified as negative. And I want you to think about this point. What is the impact of changing the threshold going to be on the number of true positives and the number of false positives generated by a classifier for a given data set? Okay, so you may want to pause the video at this time before we proceed. Okay, and uh, so we've already discussed it that when we have a classifier, we can express it mathematically in a very abstract manner that takes a certain example and it has a certain set of parameters, let's say weights and biases, and use these parameters to generate a prediction score for a given example, x, which we then discretize or binarize uh, based on a certain threshold. Let's say we can say that if fx is greater than zero, then we generate a positive prediction. And if it is less than zero, then we say that this is a negative prediction. So here zero is acting as a threshold. Now, if I increase this threshold, the question that I asked was, if I increase this threshold, let's say if I express this rule like this, if threshold is t, then is if the prediction score is above t, then the prediction is going to be +1, otherwise it's going to be -1. If I increase this threshold from 0, can you guess what is the impact of that going to be? Is the number of true positives going to increase? Is the number of true positives going to decrease? And I really want you to understand the impact of this simple value, this particular threshold value, right? If and I hope you are able to understand this concept, because accuracy is dependent upon the choice of threshold, because changing the threshold is going to change the number of true positives and false positive predictions. That means it's going to change the value of the accuracy. So accuracy, the value of accuracy is a function of, or it is dependent upon this threshold value. Okay, so we have got a classifier, but when we are using accuracy, the underlying assumption is, or the implicit assumption is, that that accuracy is being computed based on a certain threshold that is being used for binarization. If the threshold is set too high, the number of true positives and false positives, or true false positives and false negatives is going to change, and that's going to change the accuracy. So we say in general that the accuracy of a classifier is parameterized by this threshold, or is dependent upon this threshold. Okay. And I want you to do two thought experiments. So consider the following data set. Assume that the data set is balanced. That is, we have got an equal number of positives and negatives. And then consider a random classifier. So a classifier that spits out random scores for a given example, right? So within the range of, let's say, -infinity to +infinity. What is its accuracy going to be? And I want you to think about this and answer this question. And we can have a discussion on that in one of the live sessions as well. Similarly, consider a classifier which generates a score of +1 for all inputs. What is its accuracy going to be? Okay, so I want you to go ahead and solve these two examples. Let's say you can work these out. So if you got a classifier that has uh, if you got a data set that has n examples in it, and out of these n examples, p is the number of positive examples and n is the number of negative examples. And for each of those examples, the classifier you have is a purely random classifier. So it spits out these random numbers within the range of, let's say, -infinity to +infinity. What is its accuracy going to be? Is it dependent upon the threshold or not? Okay. And similarly, what happens if we have a classifier that spits out a score of +1 for all the examples that we have, what is its accuracy going to be? This simple thought experiment is going to help you understand the concept of and the underlying assumptions behind accuracy. Okay. And here's the other example, thought experiment that I want you to play with in your head, and you can also use uh, 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 paper and pencil. Let's say the data set that you have is imbalanced. That is, the number of negative examples is much, much larger than the number of positive examples. And in this case, if you've got a random classifier, much like the one we discussed previously, that generates, for a given example, random scores from -infinity to +infinity, what is its accuracy going to be? Similarly, what is the accuracy of a classifier for this particular problem going to be if it produces a score of +1 for any example that it gets? So please go ahead and work those out. Those are going to help you understand the concept of the underlying assumptions behind accuracy. Just to summarize, I've told you that there are three assumptions underlying accuracy, at least three assumptions. The first assumption is that the data set is balanced, that is, there is an equal number of positive and negative examples. The second assumption is that the misclassification of any class is equally bad. So, a positive example being misclassified as negative, or a negative example being misclassified as positive is equally bad. And the third thing that we have identified is, or what I've told you is, that the threshold, the accuracy of a classifier is parameterized by the threshold. So it's dependent upon the threshold of that classifier. Remember, the threshold of a classifier is used to convert the real valued output of the classifier, or the floating point output for computer scientists, uh, to one or -1, or to binary labels. And I've said that the accuracy of a classifier is dependent upon that threshold. I welcome you to understand and identify where do these assumptions arise, and I want you to think on these yourself, and arrive at essentially trying to identify where these assumptions originate, right? Especially the third one. And these thought experiments that I've given you are going to help you in that endeavor. Okay, thank you.